Hello, welcome to Module 7 of the course on application of spectroscopic methods in molecular structure determination. In Module 6, we considered the second order effects on the NMR spectrum. The second order spectra are fairly complex, and we saw many examples of the second order spectra. We also realized how difficult it is to get the delta values and J values from second order spectra. In this module, we will consider certain techniques that are used for the simplification of second order spectra. Typically, second order spin systems such as ABC, ABCD, AA prime, BB prime are difficult to analyze for the purpose of extracting the information about chemical shifts and coupling constants. There are several techniques available to simplify the second order spectra. Some of the techniques we will consider in this particular lecture. First, one can record the spectrum on a higher frequency spectrometer and make the spectrum look simpler because of the high frequency spectrometer. Secondly, one can do what is known as double irradiation experiment. One can selectively decouple spins so that from a complex spin system one can reduce it down to simpler spin system. Third point, one can use what are known as contact shift reagents. These are lanthanide based shift reagents which are paramagnetic, and these shift reagents essentially spread out the spectral information to a wider spectral width so that one can analyze the spectrum much more easily. Now, why does the high spectrometer frequency help in solving the second order spectra? Because second order effects are typically because of the fact that you have delta delta divided by J being less than 10, which is typically the value that one sees. Although J is independent of spectrometer frequency, delta delta is not independent of spectrometer frequency when it is expressed in Hertz. Therefore, a higher spectrometer frequency will help because it will increase the delta delta value in Hertz and thereby decrease the delta delta divided by J. The ratio delta delta divided by J will be also increased as a result of increase in the delta delta value with the increasing spectrometer frequency. With the increasing spectrometer frequency, the delta delta increases in Hertz. As a result of that, the delta delta divided by J is also increasing. J being constant, which is irrespective of the spectrometer frequency, it will be the same. So let us consider a simple example of two mutually coupled spin system. Let's call it as a AB system, separated by about 1 ppm chemical shift with a coupling constant of 10 Hertz. In a 60 MHz NMR spectrometer, the delta delta will be about 60 Hertz and the J value is 10. So the delta delta divided by J will be around 6, which is typical second order effect is what one would see in the spectrum. However, when you move to a 600 MHz NMR spectrometer, the delta delta would be 600 Hertz, and when it is divided by 10, you get a number 60, which is well within the first order domain of the NMR spectrum. So you can see from this how the change in the delta delta value with increasing spectrometer frequency helps in increasing the delta delta divided by J, that ratio delta delta by J, to a higher number, thereby reducing the complexity of the spectrum. Now what I mean is graphically represented in this particular slide. A second order AB spin system in a 60 MHz NMR spectrometer can easily become a first order AX spin system in a 500 MHz NMR spectrometer. From a visual inspection, one can say this is a second order spectrum because the inner lines are much taller than the outer lines. The intensities are not as per the expectations that one would have for a doublet of a doublet. On the other hand, if you go to a higher spectrometer frequency, you can see this doublet has almost equal intensity and this doublet also has almost equal intensity. While one cannot easily take the center of the peak as the chemical shift value in the top case, one can reasonably approximate to the center of the peak, center of these two peaks, which are the chemical shift values for the delta A and the delta B respectively. So higher spectrometer frequency essentially reduces the complexity of a second order spectrum to a first order spectrum. This is clearly illustrated in the case of the 4-chlorobutanoic acid. If you consider 4-chlorobutanoic acid 60 MHz NMR spectrum, which is the top spectrum that is shown here, The CH2 signals are essentially merging on top of each other, and there is very poor resolution. This is a typical second order spectrum for any alkyl chain of this kind. The CH2 that is attached to the chlorine has a higher chemical shift value because of the electronegativity of the chlorine. However, the other two CH2s are essentially merged on top of each other. Now, when you go to a 200 MHz NMR spectrum, there is a better resolution, as well as there is a separation of chemical shift values in this NMR spectrum. The chemical shift value expressed in delta is essentially same, but the spectrum is spread out because of the scan width will be higher for the same chemical shift ppm expressed in the scale here. Now, when you go to even higher spectrometer frequency, namely the 500 MHz NMR spectrometer, the spectrum is well spread out, and this is a very characteristic first order spectrum. So, what was originally a CH2 appearing as a second order spectrum in this top case, 60 MHz case, has now resolved into a well defined first order spectrum. For example, the central CH2, which is flanked by two other CH2s, appears as a nice quintet with the intensity ratio that one would expect for a first order kind of a quintet in the NMR spectrum. Now, let us take another example. This is the spectrum of menthol. Menthol is a terpene, it is an alcohol, and except for this particular hydrogen which is attached to the OH carbon, all the other hydrogens are essentially aliphatic hydrogens, and they appear as a bunch of peaks in the region between 1 to 1.5 ppm or so. So, this is a 80 MHz NMR spectrum of menthol. This is a 200 MHz NMR spectrum of menthol. This is a 360 and a 600 MHz NMR spectrum of menthol. As you go from 80 to 600 MHz NMR spectrum, you can see for the same chemical shift width expressed in parts per million, the spectral width is much larger here. For example, a 3.4 ppm spectral width is about 272 Hz in the case of the 80 MHz NMR spectrum. The same spectral width of 3.4 ppm is about 2040 Hz in the case of a 600 MHz NMR spectrum. So, the spectrum is well spread out, which means that delta between any two hydrogens will be much larger. J values being constant going from 80 MHz to 600 MHz. The delta divided by J ratio keeps increasing as you go from 80 to 600 MHz NMR spectrum. So, this is advantage of recording the NMR spectrum in a high frequency spectrometer, because it simplifies a second order spectrum into a first order spectrum. Another example is shown here. This is a spectrum of dimethoxybenzaldehyde. This spectrum we have already seen in the earlier module also. This is a 100 MHz NMR spectrum, and this is a spectrum recorded in a 200 MHz NMR spectrometer. As you can see here, the peak intensities are much better here. They are more or less equal intense between the doublets, unlike in this case, for example, with the intensities are very different. So, the spectrum is tending to be not exactly a first order spectrum, but it is tending to be a first order spectrum as you go from 100 to 200 MHz. The same sample, if one were to record it in a 600 MHz spectrum, it would be a typical first order spectrum. Now, the second technique has to deal with the selective irradiation or the decoupling experiment. What happens in this experiment is irradiation of a particular spin selectively using a second radio frequency source can lead to the saturation of that particular spin. In other words, you are promoting the spins from the ground state to the excited state, in other words from the alpha state to the beta state, and in the process, if you continuously irradiate the sample at that particular frequency, that spin will get saturated. In other words, the population becomes equal, and it is different from the equilibrium population that one expects. Now, this will result in two things. One is the disappearance of the signal, because there is no longer excess population in the ground state. So, the signal will vanish essentially because of the saturation of the alpha beta spin states. The second thing that will happen is the decoupling of that particular spin from the rest of the spin in a mutually coupled system. In other words, under equilibrium condition, the spins will be mutually coupled. When you saturate one of the spins, that undergoes a decoupling with the rest of the spins, and as a result of that, the spectrum simplifies with less number of mutually coupling partners. To illustrate an example here, if you take an ABC system, this is a 3-spin system which is mutually coupled to each other, so it will present as a second order spectrum, fairly complex spectrum. Suppose if one irradiates the spin C, in other words, use a second radio frequency corresponding to the frequency of spin C, hydrogen C, let us say for example, it will saturate that particular hydrogen spins, and as a result of that, decoupling takes place. So as a result of that, the ABC system simplifies to an AB system, which is a two-spin system which is mutually coupled. An AB system is much easier to analyze. We know the methodology to analyze an AB spectrum much better than analyzing an ABC spectrum. So as a result of that, although it is still a second order spectrum, it becomes a more easily analyzable second order spectrum in terms of the less number of chemical shifts and coupling constant that one has to deal with to obtain this information from the spectrum. Now this is illustrated in this particular example. If you take a two-spin system, essentially you have an AB kind of a pattern that you see in the NMR spectrum. Now, when a double irradiation frequency is applied to this particular signal here, that signal completely disappears and this signal collapses to a singlet. Similarly, if one applies a second radio frequency corresponding to this particular spin here, this hydrogen here, that signal collapses completely and this signal reduces to a singlet. So an AB quartet can essentially become a singlet spectrum when B is decoupled or A is decoupled. This is even more useful when you have an ABC spin system going to an AB kind of a spin system. Alkenic hydrogens will present a fairly complex spectrum. This spectrum we have seen already earlier. This is a spectrum of methyl acrylate. This is an ABC spin system. The C is shown separately in this right hand side of the spectrum. This is a fairly second order complex pattern is what one sees here. Now, suppose if one applies a radio frequency corresponding to the frequency of C, which is approximately in this region here, that will essentially result in decoupling of the C with the A and B. So A and B will present simply as an AB spectrum. AB spectrum with a 4-line pattern like this is much easier to analyze and extract the information corresponding to delta A, delta B and JAB. Now if one applies a frequency over here, the second frequency when it is applied here, then it will become a BC spectrum, which is also a second order spin spectrum, two-spin spectrum. So it is easy to analyze such two-spin spectrum much more readily compared to a three-spin system, which will be a fairly complex spectrum like it is shown here. Another example of a ABC going to an AB spin system. If you observe this particular multiplet which is appearing in the left hand side, that is mutually coupled to this multiplet here and this multiplet here. So when a second radio frequency is applied and this multiplet is decoupled or saturated, that signal completely vanishes, and also you can see the two starred multiplets which are originally a multiplet, second order effect multiplet is what is seen. Now it appears as an AB quartet. AB quartet can now easily be solved because it is easy to extract the information from an AB quartet rather than a complex multiplet pattern like this one. Lastly, we see the effect of contact shift reagent, otherwise known as Lanthanide shift reagents. Lanthanide shift reagents are very useful for stereochemical determination. We will deal with this aspect of the Lanthanide shift reagent in a different module, but for the present purposes, it is a paramagnetic lanthanide complexes with beta diketonate as the ligand. In other words, they are chelating ligands. These are contact shift reagents. They must coordinate to a basic site in the substrate. In other words, they must coordinate to either an oxygen lone pair, nitrogen lone pair, or a sulfur lone pair. Kind of a functional group must present in the molecule in order for these shift reagents to work, because they form a weak complex with the substrate and then affect the shifts which are induced shifts as a result of the contact. Now the induced large shifts in the chemical shift values of various proton is what one measures in the contact shift reagent studies. So the induced shifts depends on the lanthanide ion concentration, its angle and the distance as defined in the next slide. We will show this in a minute. These are the structures of commonly used lanthanide shift reagents. You can see here each one of these ligand is a beta diketonate kind of a ligand, and three such ligands are chelating to the lanthanide ion. The usual lanthanide ions that are used are europium 3+, praseodymium 3+ are the ions that are normally used in the case of lanthanide shift reagents. This is a chiral lanthanide shift reagent. This is extremely useful when one wants to analyze enantiomeric mixtures of compounds. In other words, racemic mixture of compounds can be analyzed using a chiral shift reagent. We'll see some examples of use of chiral shift reagent when we talk about stereochemical aspects by NMR spectroscopy. Now this is a relationship which is called a mecanol relationship. The delta nu is the difference between the chemical shift value without the shift reagent added to the chemical shift value with the shift reagent added. And nu is the frequency without the chemical shift reagent being added. Now these parameters, the k is a constant, 3 cos square theta minus 1 by r cube essentially relates to the ratio of the induced shift, which is delta nu divided by nu. R is the distance between the lanthanide ion and the contact to the hydrogen which is under observation, for example. Now the lanthanide ion is complex to an oxygen lone pair, and it is now at a distance of r from the hydrogen which is under observation, and this is the angle between the oxygen, europium and the hydrogen is the theta, which corresponds to the theta in this particular equation. So one can readily see that the lanthanide shift is essentially inversely proportional to the power 3 of the distance. In other words, as the distance increases, the induced shift falls off quite rapidly. In other words, the closer the hydrogen to the europium center, larger will be the shift of the induced shift of the chemical shift as a result of the lanthanide shift reagent. Here is an illustration of the effect of lanthanide shift reagent on heptanol. This is hexanol. You can see the hexanol spectrum being shown without any lanthanide shift reagent being added as a normal spectrum, essentially except for the CH2OH functional group, where the CH2 is attached to oxygen, which is an electronegative element, which comes around 3.5 ppm. All the other aliphatic hydrogen essentially appear as a fairly complex multiplet, as a bunch of peaks which are unresolved peaks, for example, in the region between about 0.8 ppm to about 1.5 ppm or so. So the whole bunching of these aliphatic hydrogens cannot be resolved without addition of the shift reagent. When shift reagent is added, about 6.5% of europium FOD3. FOD3 is the beta ketonate, one of the beta ketonate ligands. The europium complex, when it is added, it complexes to the oxygen, and you can see here the shift of the hydrogen of the CH2OH from 3.5 ppm to about 6 ppm. This is the induced shift that we are talking about, delta, and this can be expressed in Hertz if you know the spectrometer frequency of the spectrum that is being recorded. Now you can see also all the other peaks which are bunched up together here. Now they are getting resolved as a result of the induced shifts of the various hydrogen. Once the europium is coordinated here, with respect to the europium, each of these hydrogens are having different distances. As you go further away and away from the europium, the shift is going to be reduced. In other words, this CH3, which will appear as a triplet, which is appearing here, essentially remains in the same position. A very little shift is taking place, whereas the CH2OH, where the CH2, which is attached to oxygen as well as europium, has the largest shift. In other words, as the distance increases, the induced shift falls off quite rapidly. Here is another example. This is 6-methylquinoline is the example that is given. The bottom spectrum is essentially without the addition of the europium shift reagent. The spectrum is measured in CdCl3 as a solvent. You can see here the hydrogens of the aromatic ring here, hydrogen 3, 4, 5 and 7, they all bunch together and appear as a multiplet in the region between 7 ppm to 8 ppm. Only the hydrogen which is adjacent to the nitrogen, because of the electron withdrawing effect of the nitrogen, it appears separately as a multiplet around 8.9 ppm or so. Upon addition of the shift reagent, will coordinate to the nitrogen lone pair here. So as a result of that, hydrogen 2 and hydrogen 8, which are in close proximity to the europium, they get shifted further downfield in the NMR spectrum. For example, the hydrogen 2 now comes around 14.5 ppm, whereas the hydrogen 8 now comes around 13 ppm or so. Not only that hydrogen 8 is now resolved, you can also see the multiplicity very clearly. One can obtain the coupling constant information fairly readily from this. One cannot obtain the chemical shift value because the induced shifts are now very different in each one of the spectrum depending upon how much of the europium shift reagent is added. So the chemical shift information is not very useful. Nevertheless, one can see the multiplicity pattern emerging to a simpler multiplet pattern which is easily analyzable. So the addition of a shift reagent can actually simplify a second order spectrum to a simple first order spectrum. Another example would be an AA prime BB prime spectrum, which is a fairly complex spectrum. Take the example of the CH2 which would appear as the AA prime BB prime spectrum in this particular ketone. Indeed, it appears as a multiplet as shown in the spectrum here. When shift reagent is added, it will complex to the oxygen lone pair. As a result of that, now the chemical shift is going to be spread out, and this will essentially now become a first order system, because the chemical shift difference between the two CH2s are going to be much more when the shift reagent is added. The J remains constant irrespective of the shift reagent. So as a result of that, the delta divided by J is going to be much higher after the addition of the shift reagent. So what was originally a complex multiplet now has resolved into two triplets, which are much easier to analyze in terms of extracting the J value information from this spectrum rather than from this spectrum. So essentially what has happened is, after the addition of the shift reagent, what was originally an AA prime BB prime system has simplified itself to an A2 X2, such that the A2 appears as a triplet and the X2 also appears as a triplet in this particular instance. So what we have seen in this particular module is simplification of second order spectra by three different techniques. First, using a high resolution, high frequency NMR spectrometer, which essentially increases the delta to J ratio to much higher values as the spectrometer frequency